Friends, welcome back to my YouTube channel. In this video we are going to discuss the exception handling design pattern. So you will learn what exception handling design patterns are, why they are important in real world software systems, and common patterns used to handle error cleanly and effectively. So without wasting any time, let's get started. So exception handling. So what is exception handling in agentic design pattern? So what makes a system agentic? So agentic systems. So first, what makes a system agentic? So it calls LLMs. So LLMs are probabilistics. It is not deterministics. The same prompt can produce different outputs, and they can hallucinate, refuse or misunderstand the context. So this means the outputs are never get generated. It's a very guaranteed way to be corrected, right? So that is called LLMs. Next is invoke tools or API. So agent call external systems like database, search API, payment gateway, internal services. So these systems can be timeout, rate limit, change schema, return partial or invalid data. So external dependency fails regularly. Chain multiple agents. So one agent output become another agent inputs. For example, if we talk about the planner, then it goes to the retriever, then it goes to the reasoner, then it goes to the executor. If one agent fails silently, the next agent works on corrupted inputs. So error propagate and amplify it. So failure multiply across the chains. It runs. So no human watching at each steps. So no manual retry decisions, and there is no intuition based stoppation. So the system must decide by itself, means when to try, when to stop, when to escalate. So that the failure are expected, it's not edge cases. So this is the most important idea. So in if we talk about the traditional software, so failures are rare, usually caused by bugs, and they fix the bugs, and then we can redo the deployments. So in agentic systems, if the failure happens because of LLM reasons imperfectly, APIs are unstable, data is incomplete, and maybe environmental change also. So failure is normal operating behavior, not an exceptions. So what happens without structured recovery? Okay, so what happens? So for that, uh, so agent loop infinitely. So agent retry the same action with the same prompt again and again against the same failing tools with no retry limit or learning. So for example, LLM hallucinations, tools fails, retry, and then same hallucination is happening. So infinite loop burns compute and APIs. Hallucination increase. Agent treats LLM output as a truth. Even when it's wrong, its downstream agent trusts it, and error turn into facts. The system becomes confidently wrong. System become brittle. So one failure break the whole workflow. No fallback path and no partial success. And then finally there is no graceful degradation. So same issue cause full systems collapse. So like if we talk about the cost explodes. So if the LLM is repeated calling LLM calls with the help of too many threads where multi-agent amplification is happening, infinite loop execution is happening there. So for example, one failure, 5 tries, 4 agents into LLM, so all R is multiple. Okay, see how much cost it will be. So agent failure are expensive failures. Okay, so agentic systems must have failure detections, error classifications, retry limit, and fallback paths. And without these agentic AI systems, don't fail fast, don't fail safely. Means fail loud, long, and expensively. So, in one line, I can say agentic systems are control loop operating in unreliable world. A structure recovery is the best control system that keep them safe. Next is observability and matrices. So, so the answer is observabilities. So measuring what agent actually do when things goes wrong. Why observability is non-negotiating for agents. So agent systems are region instead of following fixed code paths. It acts autonomously. It fail in a unpredictable way. So if we go with without matrices, so failure may be failure maybe stay in visuals and hallucination looks like a very success and cost goes very silently. So if you cannot measure agent failure, you can't trust anatomies. So what you track and why each matrix matters. So first is retry count. Means how many times an agent retries an action. And high try high retry counts indicates unstable tools, bad prompts, and infinite loop risk. So if the number of retry count increasing, then we are wasting the compute and the costs. Failure types. So why it what it measures? So it measures the category of errors. For example, LLM reasoning, tool APIs, data error, rate limits, and policy violations. So it's tell you what kind of failure dominates. Let's let's you fix root cause instead of symptoms. So what is the signal? What is the benefits we are getting here? So many LLM errors that increase prompt model issues, and many API errors that has external dependency problems. Fast track uses. So it means it measures how often agents switch to backup models, alternate tools, simplified plans. So high fallback uses means the primary path is unreliable, system is surviving, not thriving. Next is hallucinations. It's measure the how often LLM outputs are factually incorrect, unsupported by retrieved data, and contradicted by the tools. So it is why it is important. So hallucinations corrupt downstream agents and it create false confidence and hard to detect without matrices. So rising hallucination rate that having anatomy risk. MRT. Average time from the failure is having the stable recovery. So it shows how fast your system self heals. Long MRT, we can say long MRT is equal to slow retrieves and poor fallbacks. So finally, if we talk about MRT, means if we have the high MRT, then bad user experience and high costs. So why these matrices tell you the real value? What? So what? Where the agent fail? By collecting the failure types, retry count, MRTs. So you so this is the uh, this in this way the metrics tell you the real value. Where agent fails, which tools are brittle. If a tools show high retry count, high fallback uses, and long recovery times, then the tool is unstable, the schema may be changing, and then the integration is fragile. So it should be replaced, hardened, or isolated. When autonomy become unsafe, this is the most important insights, that it gives the warning signs: rising hallucination rate, increasing retry per task, frequency escalation, and growing MRT. So these signals means the agent is no longer making reliable decision on its own. Okay, so so if we talk about like the observability and matrices, so this observability is a safety dashboard for anatomy agents. If we go without it, so agent will fail silently, cost explode invisibly, hallucination looks like success, and anatomy become a liability. If I go with observability, so the failures are visible, recovery is measurable, anatomy is controlled, not the blind. So in one line I can say, um, if you don't track how agent fails and recovers, you should not let them run at autonomously. Next things, exception classifications. Before an agent can recover, it must understand what kind of failure to occur. Retrying without understanding the failure is dangerous in agentic systems. So, exception classification is where enables the safe retries, intelligent fallback, control autonomy, and cost containments. And the fallback prevents the total failures and keep the agent partially useful. But the fallback only works if agent knows why it fails. So before recovery, the agent must understand the failures. So the error, what is the error categories we have? So first is transient. So it's like a network timeout, temporary service outage. So what is happening? The system is healthy, the environment is temporarily unstable, and retry is yes. Second is the rate limit error. So it shows HTTP 429 errors, and retry is yes, it retry. So the correct recovery is pause, exponential backoff, and reduce request rate. Why native retry fails? It because intermediate retry makes the problem worse, can try in bans or throttling. Total errors, it's having the bad API response, and retry it's maybe. So it validate the input and output and to try alternate solutions. Next, LLM errors. So it's having hallucinations and refusal, and retry logic, it's prompt fix. So it adjusts the prompt, reduce temperatures, and it constrains output format, and if required then it switch the models. Data errors. So it's missing required fields, corrupted documents, empty retrieval results. And what's happened? The agent lack of required informations we have. Retry logic, no, it will not work. So ask user for missing data and request clarifications for that, and stop execution safely. Logic error, that is infinite loops. In repeated failed steps is happening. So agent reasoning or planning is broken. So retry logic is stopped. And correct recovery, how can we recover? So it terminate execution, log failure, and trigger redesign or human reviews. Next is security and policies, PIA and restricted. So it here the PII expose restricted content and compliance and violations. So retry is never, it is escalated. So the correct recovery is stop immediately, escalate to human, log in, log and audit it eating. Right. Next is fallback strategies. So the fallback prevents total failures and keep the agent useful even when something breaks. In agentic systems, the failure is inevitable. So fallback decide what agent does next instead of crashing or looping. So the failure prevent tool failure and keep the agent useful. So the agentic systems it rely on probabilities LLM reasonings is depend upon on unreliable tools and API and it operates autonomously without human watchings. If we go without fallback, so once the failure one failure is equal to complete task failure, an agent get stopped and retrying, and there and after that the cost explodes. Right. The common fallback, LLM hallucinations. What fails here? LLM produce incorrect or fabricated output. It's often caused by overlay, open prompt, high temperature, missing grounding context. The what would be the correct fallback? It's tighten the prompt, add constraints, lower temperature, and is focus structured output. So as a result, the LLM reasoning become more deterministic and reliable. LLM down switch model. So why it is fail? So LLM service is unavailable. It's having the timeout, outage, and quota exhaustions. So when relying is risky, retrying is risky. When having downtime, maybe last minute, retry waste time and money. And the correct fallback switch to backup model, a small models and local models. So the here the availability is greater than the perfections, you can say. Tool failures, the alternative tools. So why it fails? So API return invalid response, tool switch changed, tool is unstable, and due to that deterministic failure repeats. And the and if we talk about the correct fallback strategy is use alternate data source, use catch results and API, similar API. As a result, the lower accuracy and higher reliability is coming. Retrieval failures. So it's having the some kind of issue in vector search or return, okay, and embedding missed relevant content. Index is stale. We have so used a keyword or proper keyword and lexical search. Use a broader query and search raw documents. And here this planning it failed due to agent overplanned, multi-step reasoning is break and dependency conflicts. So here we need to reduce the steps, use direct reasoning and solve subset of the task. And next is the full failures. This should be asked from human. Why it will fail? So all automated strategies failed. Confidence is in output is low and safety and correctness at risk. So why this is essential? So uh, autonomy must have limits. Humans are the final safety nets. And if we talk about the correct fallback, so it should be escalate and ask the clarifying questions here. Next is backup strategies. So backup study is only for recover errors. Backup is not the generic retry mechanisms. It is a control mechanisms that protects external systems, the agent itself, your costs and reliabilities, and why create backoff is essentials. Why? Why backup is critical in agentic systems? So agentic systems are retry autonomously, call it limited API, and trigger failure scale. If you go without a backup, so agent retried instantly, failure cascaded, and then system got throttled, and the cost spike again. And so backup ensured that retrying is delayed and controlled, and system have time to recover, and agent does not overlap dependencies. Let's talk about the backup types, when and why to use each. First one is the fixed delay. When to use simple tools and internal services. What it does. So it waits a constant amount of time before retrying. Means if you talk about the flow, then fails, then it wait for 5 seconds, then retry it. So why it works here? So internal tools are stable, failures are short-lived, and traffic volume is low, and it having the risk it can still cause retry spikes, no suitable for high scale APIs. Exponential, that is talk about external API and LLM calls. So it increase delay after each retry, means 1 second, 2 second, 4 second, 8 second, and then stops. So why it works? So it gives external system time to recover. It reduces retry pressure quickly and in a steady standard for the API. So why it is essential for it? So LLM providers enforce strict rate limits. It's immediately retry increase throttling. Exponential plus jitter. So if we have a large scale of distributed systems, so it's add randomness, means jitter means randomness to the exponential delays. So if the formula is could be delay is equal to base into 2 k power n plus minus random noise. So why jitter matters? If you go without jitter means randomness. So so why without jitter, the thousands of agents retry simultaneously, and it's called retry storms. But if we go with jitter, then retry spread out and system stable very faster manner. So it's where it is very critical. So that this is critical in multi-agent platforms, enterprise scale AI systems, high QPS environments, adaptive, that SLA awareness systems, production and critical systems. So this is dynamically adjust delay based on error rate, latency, and then cost budget and SLA targets. So if we talk about the example here, so increase delay during the peak load, and it reduce retries when nearing cost limits, and it stores retry if recovery time exceed SLA. Why it is very powerful? So it optimizes reliability and cost, and it prevents over retrying when success is unlikely, and where we cannot use this backup. So this is not used for logic error, hallucinations, and missing data, and security and policy violations. So retrying this waste time and money. Next is the architectural design flow for exception handling. So it start from user goals, so goal intake and the planning layer. So what happened? The user goal is parsed, planner agent decompose into the steps, and execution plan is created. Next is the failure mode. Ambiguous goal, and why it is failure mode? So ambiguous goal and over complex plan. And recover is talk about replan, re-asking clarification questions. And second layer, the execution layer, where the most failure happens here the, here. So this is where the call an LLM use tools and its external API. And if you talk about the execution steps, so it's from LLM, then tools, then API. And typical failures here, it's like it's LLM failure means hallucination happened. Tool failures means a schema mismatch. API failures means timeout error. And infra side also you can say like network error. So failure are expected, not the exceptional. Next is the execution capture layer. So critical boundaries here. So every action is wrapped like this, means why it is matters. So it prevents silent failures and stop and control retries, and it prevents systems state. So no action should fail without being classified. Next is exception classifications here. Exception classification, the brain of the recovery. The system understand the failures, not just the react. So the flow, it looks like error, then it's classifiers, then error categories. And the typical class can be transient, that having timeout, rate limit, LLM reasoning, data error. And this step decide what is even allowed next. Next is recover in decision engines. It is a policy driven. So this is the decision table, not hard coded retries. Next is Backoff controlled retry safety. So if retry is allowed, then why backup is mandatory? So it prevents API bans, avoid retry storms, and it reduces cost spikes. So the cost control is equal to backoff plus retry budgets. Next is the fallback strategy, the gracefully degradations. So why retry is not enough? Agents degrades immediately. For example, switching LLM from GPT-4 to GPT 3.5, switching tools, use cached data, use simple reasoning, partial answer. Next is reflection and self-link layer advanced. So after recovery of failure, what failed and why it is failed? What should change next time? So agent updates the prompt plan and tool choices and retry strategy. So this prevents repeating the same mistakes. Next is termination and execution layer, kill switch. So if recover fails, it stops executions, and log failure escalate to human. And why stopping is important? So it prevents infinite loops, prevents hallucination chains, and prevents runaway costs. So if we talk about the end to it control flow in one line, so first it will plan, then it goes to action, then it goes to fail. So fail having for what? If it is yes and no, and then after fail it's having the classify, then decide, then having the retry, back off, fallback, then stops. So this is the minimal architecture for production grade agentic AI. And so this agentic system are control loop, not chat flow. Exception handling is the control systems that keep autonomy safe, reliable, and affordable. So this is all about this architecture of exception handling agentic design pattern. So that's all for the video. If this video helped you to understand exception handling agentic design pattern, don't forget to like, subscribe, and share. See you in next one.